Good morning, everyone. Today, we begin our exploration of motion trajectory preview planning. This is a foundational concept for modern intelligent motion systems. Imagine a robot, a self-driving car, or a CNC machine. Traditional planning methods often work step-by-step, focusing only on the immediate next move. Preview planning changes this paradigm entirely. It enables the moving system to look ahead, to forecast its future state multiple steps into the future. By performing optimized calculations in advance and continuously sending instructions through a buffer, the system can achieve smoother, safer, and far more efficient motion. In essence, it shifts us from static, reactive path planning to a dynamic, rolling, and continuously optimized planning process. This proactive approach is key to achieving high performance in complex, real-world environments. The backbone of preview planning is typically Model Predictive Control, or MPC. Think of MPC as a smart, closed-loop cycle of planning, executing, getting feedback, and replanning. The first critical component is the prediction model. This is the system's eyes. It is a mathematical representation, like a kinematic or dynamic model, that describes how the system behaves. For example, a car might use a dynamic model, while a drone uses a kinematic one. This model answers a crucial question. If I apply a certain control input now, like turning the steering wheel or increasing throttle, what will my state be in the next few seconds? This predictive capability is what allows the system to peer into the future and evaluate the consequences of its potential actions before executing them. The second core component is rolling optimization. At every single control cycle, which could be every hundredth of a second, the planner takes the system's current state as the starting point. Using the prediction model, it computes the best possible sequence of control actions for a limited future window, known as the prediction horizon. But what defines best? This is determined by a cost function. The optimizer aims to minimize this cost, which typically includes several factors: tracking error, how far we deviate from our desired path; control effort, we want actions to be smooth and efficient to save energy and improve comfort; adherence to hard constraints like speed or acceleration limits; and penalties for violating soft constraints such as getting too close to an obstacle. The planner essentially solves this optimization problem repeatedly, always with the latest information. The third pillar is feedback correction. Here's where the rolling optimization truly comes to life. After solving the optimization problem, the system does not blindly execute the entire plan sequence. Instead, it only implements the very first control command from that optimal sequence. Then, it moves to the next control cycle. At this point, new sensor data comes in, updating the system's actual state, perhaps revealing a slight model error or an unexpected disturbance. The planner then takes this new, real-world state and performs the optimization all over again from this fresh starting point. This continuous loop of planning one step, executing it, measuring the outcome, and replanning is what gives MPC its robustness. It allows the system to correct for inaccuracies in its model and adapt to the unpredictable nature of the real world. Let's make this concrete with a key application: autonomous driving. Picture a self-driving car on a city street. Its sensors detect a bicycle moving slowly ahead. The system doesn't just react, it predicts the bicycle's likely path for the next 5 seconds. Now, the preview planner kicks in. It formulates an optimization problem. Over this 5-second prediction horizon, how should we control the steering and throttle so that the car 1 stays centered in its lane, 2 maintains a safe distance from the bike, 3 ensures a smooth, comfortable ride, and 4 never exceeds speed limits? The planner solves this problem, generating an optimal trajectory and control sequence. The car then executes the first command, maybe a slight steering adjustment and gentle braking. In just 100 milliseconds, with new data on the bike's position, the entire cycle repeats, allowing for seamless, safe, and adaptive driving. Now, let's consider industrial robotics. Take a robotic arm performing high-speed pick-and-place operations. Preview planning here means the system doesn't just plan the path from point A to point B. It also pre-plans the complete velocity and acceleration profiles for the entire movement. The benefits are significant. First, It avoids jitter and overshoot by optimizing acceleration in advance, leading to smoother motion and less mechanical stress. Second, it improves cycle time by calculating the fastest possible trajectory within the robot's physical limits, like torque and speed constraints. Third, it enables dynamic obstacle avoidance. If a vision system predicts a worker might enter the workspace, preview planning can initiate a smooth deceleration or a path change well in advance, moving beyond the need for last-second, jarring emergency stops. This enhances both safety and efficiency. Despite its power, preview planning faces significant challenges. First is computational complexity. Solving constrained optimization problems online, in real time, is demanding. This is especially true for systems with many variables or long prediction horizons. The field relies on efficient solvers and clever algorithms to make this feasible. Second is prediction uncertainty. Predicting the behavior of others, like pedestrians, is inherently uncertain. Advanced methods now use stochastic or robust MPC to explicitly account for this uncertainty, creating plans that are safer, if sometimes more conservative. Third, obstacle avoidance often leads to non-convex optimization problems, which are difficult to solve perfectly. Researchers tackle this by simplifying problems into convex forms or combining optimization with search methods. Finally, a major frontier is integration with learning, such as using neural networks to learn better prediction models or reinforcement learning to discover optimal planning strategies for complex, rule-defying scenarios. In summary, motion trajectory preview planning is a core enabling technology for intelligent, autonomous motion. Its essence is elegantly simple. Use a model to predict the future, use optimization to find the best plan under multiple constraints, and use feedback to correct for reality's imperfections. This dynamic, rolling approach is what allows modern systems, from self-driving cars and drones to industrial robots, to move not just autonomously, but deftly, smoothly, and safely. The future of this field is incredibly vibrant, pushing towards ever faster computations, more accurate environmental predictions, greater robustness against disturbances, and deeper fusion with artificial intelligence techniques. This convergence will undoubtedly unlock new levels of capability for intelligent machines. Thank you for your listening. This is the end of session 19.